in this block on strategies to identify cause and effects in education economics. You already got to know randomized controlled trials, we talked about instrumental variables approaches, differences, and today is the regression discontinuity design. Who of you has already heard about regression discontinuity design or RDD? Okay. In which context?
By Professor Mark Steinhardt, and in his course America Economic History and etc. Yeah, that was included. Yeah.
I read a few papers in development economics.
Yeah. So you see, it's a strategy that's not just used in education economics, but also in other fields of economics, like development economics, area studies in general, and it's even broader. It's not just used in economics, but also in other social science disciplines, in particular in political science, in many applications. Okay, but what is regression discontinuity design? Well, the idea is that we are living in a world that has many rules, and some of these rules are kind of arbitrary. And they induce a kind of natural experiment that we explore. And one way to exploit them is in terms of regression discontinuity design. So there must be some kind of discontinuity in the probability to receive the truth. And this can be, for instance, that in education economics we can assume that students or pupils, secondary school, they have to take like a specific test or exam, and when they fall below a certain threshold, so when they do not score enough points, they must repeat a grade, or no, let's say they get extra tutoring. So remedial lectures. So when they score less than some specific points, then they have to take extra tutoring, remedial lectures, so that they can cope. And then the overall question is, okay, so this extra tutoring, that's expensive. So we have to pay some money. Does it pay off for the individual, for the society? A huge problem when we generally analyze extra tutoring is that there's a lot of selection going on. So those individuals who kind of participate in tutoring, they select. So either because they have worse, bad grades and want to improve them, or they want to go to some very selective schools or universities later, or because they can afford paying this tutoring. So there are many reasons to assume that there's selection of treatment in observational studies. So that people select that they have to get additional treatment. Okay. So now comes the idea of this RD, and that says, well, here we have some kind of local randomization. Some students who fall below a specific threshold, they are offered, but they have to take this extra lessons, this extra remedial tutoring, extra tutoring, and others who are above that threshold, and they don't have to take. The idea is now that this kind of rule, this kind of cutoff, that induces some kind of random variation in who participates in the trend. And that's what we're exploiting in a regression discontinuity. Okay, so here we have what's called it's the test score. And this is our running variable. Another name for running variable is assignment variable. So that's all. And then we have here a test a specific cutoff. And here on the vertical axis we have the treatment probability. And treatment in our case is whether people take this remedial tutoring or lectures. Yeah? And then we see that here is maybe like 100%, and here is 0. Yeah? And then we might observe some something like this. Yeah, so this is kind of, so these are the observations around that. And then we kind of fit lines on both sides. Yeah, so what do we see here? Yeah, so we see that generally the higher the test scores, the lower the likelihood to take the treatment. Yeah, so to take this reminder lectures. But what's more importantly, at this cutoff, there's a strong discontinuity. Yeah? So scoring below the cutoff results in a jump in the treatment probability. And this is kind of what we call, where the name discontinuity comes from. Yeah? So we can't make a straight line through this. We can't draw a line through this, but there's a discontinuity. Yeah? It doesn't have to be a line, but we could also kind of here, there's not a function form that defines it. Yeah, so individuals who score just below the cutoff and individuals who score just above the cutoff, we assume that they're extremely similar. Yeah? It's maybe just a bit of luck. Yeah? That one had a bit more points, one more point, and the other a bit less. Yeah? And this rule then induces some exogenous or arguably exogenous variation. And this is often exploited in a regression framework. So where we fit lines or other higher order polynomials of the running variable on the left and on the right hand side of the cut. This is where the name regression discontinuity design comes from. This discontinuity, that's really crucial. RD, or simply call it RDD, for regression discontinuity design. It comes in two forms. Fuzzy and sharp. What I drew here is a fuzzy regression discontinuity design. A sharp regression discontinuity design would be something like we have treatment probability of 1 until the cutoff, and after the cutoff, treatment probability of 0, or vice versa. So that the probability to receive the treatment changes from 100% to 0%, or from 0% to 100% at the cutoff. That's a sharp RD. Here, in the case that I drew, so we can force no one to take this remedial tutoring, but also some individuals who are above the cutoff, they think it's better if they take this extra lesson, so they can both elect for that. You could also think about an institutional setting where we force the students who are below to take that, and only they are allowed to take it. Then we would have a sharp regression discontinuity, because the discontinuity and the treatment probability is from 0 to 100, or 100 and 0. Okay, but actually, so this is just like one step, one very important step to determine that we have this discontinuity in the probability to receive the treatment. So later we will also see there's a lot of similarity to instrumental variables estimation. So we can say, okay, this means a kind of instrument. We have some kind of exogenous variation in our treatment variable. And therefore we do have a first stage if you want to use instrumental variables language. But that's not the ultimate goal of our research endeavor. We want to know whether the treatment has actually an effect on our outcomes that we're really interested in. So, for instance, let's assume we want to investigate the effect of this extra tutoring on, I don't know, whether someone passes the grade, or if there's an end of year test or exam, what's the score on that? And this is then the first stage, and we can outcome stage. It's kind of the reduced form that we have. We can draw a very similar picture. Again, we have our running variable on the horizontal axis, and on the so the treatment probability is probability that d is equal to 1. We assume a binary treatment here, and here we have our dependent variables y. Let's say these are exam points. And then we have here the same cutoff. We have the same individuals who've been at that test before or below or above that test, and then we basically look at the distribution of their outcome variables. So let's assume it would look like this. We can give an interpretation of what I've just drawn here. So we have the cutoff here, but we see the relationship between the score in the test that was maybe at midterm, and then kind of the points in the final exam. What do these slopes mean? What does this discontinuity mean? The slopes are easy.
The slope, it's how related it is, how much you study for the midterm exam, or how well do you know the midterm exam versus, and how does that affect later to the grade of the final exam.
Yeah, and we can see that individuals with higher test scores, they also have higher points in the exam, on average. So that means kind of these test score results, they are predictive of the exam results. So that's nothing very spectacular that I drew. It's just kind of important to understand what this graph tells us. So the higher the test scores at midterm, the higher the exam points at the end. But that's not kind of what's of most interest to us, but for us, this discontinuity, I call it tau, that's very interesting, because here we see there's another discontinuity at the cutoff in our outcome variable. So we see it's a very smooth distribution, it just increases, but we see that individuals who are above the cutoff, that they score better than individuals below the cutoff. Not just because their test score is higher, but because they are above the cutoff. So when you have a regression discontinuity design or paper, it's important to first look at the first stage. Is there really a discontinuity in the treatment probability at the cut? Otherwise, you basically don't have the first stage, you don't have the paper. You call it regression discontinuity design, but there's no discontinuity. So therefore, if you don't have this first stage, you can't write a paper. It's similar to instrumental variables, and here you don't have a first stage. There's nothing that you do not identify exogenous variation in the treatment probability. That's the first graph. The second graph is different. Here we look at the substantial nature of the research question. And it could be that there's no discontinuity here. That would mean basically being below or above the cutoff does not have an effect on our outcome variable. That would be the reduced form interpretation. Or, now thinking more in instrumental variables approach is maybe that our treatment does not have an effect on the outcome variable. So that kind of this, if there was here no discontinuity, we would say that this remedial education, the extra tutoring, would have no effect on the exam grades. Okay. Now we see there is a discontinuity. What does that mean for the effect of the treatment extra tutoring? It's a bit tricky because it seems how I drew it here is a bit counterintuitive. And the reason is, we say that individuals who are below the cutoff, they have a higher probability to receive the treatment. So individuals who have fewer points on the test, they're more likely to get extra points. They're more likely to get extra lessons, extra tutoring below the cutoff, but they perform worse than those above. So this would be in line with the story that extra tutoring reduces exam points in the end. So that, I just accidentally drew it this way. But you could come up with some stories, right? That there's some kind of stigma if individuals have to go to this extra tutoring, or that in the meantime they would do some more things that are more productive for what they have. But in general, we would rather assume that the picture looks a bit different, maybe more like this. And then we here have a treatment effect and saying those who are more likely to receive the treatment, they have higher test scores. And therefore, we can, if that was kind of the graph that we drew, we would say, okay, this extra tutoring, that improved our exam points. If the graph looked like this, we would say extra tutoring is good. And now we can see again the similarity to IV, when we have a fuzzy regression discontinuity design as here. Because our final RD estimate is not this what I call tau. Here, that's just the discontinuity at the cutoff. However, at the cutoff, we don't have a sharp 100% discontinuity. Some individuals change their treatment status, but not everyone. So we have some always takers, or here, they always take the treatment, and they always take reminder lessons, irrespective of whether they're to the left or to the right of the cutoff. And we have some never takers. So individuals who don't take the treatment, the extra lessons, no matter whether they're on the right or the left of the cutoff.
One question, would you say that at the cutoffs, students would differ structurally? For example, low-income students, students from a low-income background to students from a high-income background?
So far I did not talk about the assumptions, but the assumption is that they are basically comparable to the left and to the right of the cutoff. They're allowed to change only kind of continuously. So it might be that they're more whiteboard space. Okay, the whiteboard is not really white, but I hope you can see what I want to write here. So it's basically the same graph as before. On the horizontal axis, we have the test score, we have the same cutoff, and now what we could do is that we could plot something like the socioeconomic status of the pupils that we have, or some other background over it. And basically what we so that's kind of, we basically assume here kind of what I drew is the higher the test scores, the higher the socioeconomic status. And that's kind of just what I drew here. It's probably realistic. Doesn't have to be like this linear monotones. However, coming back to your question, what is crucial is that here, at this point, there's no discontinuity. So we here, to the left, they have slightly lower SES than those to the right. However, this changes basically just continuously here with a straight line. And we're kind of so a violation would be if something else changes here discontinuously. So if this is a continuous change, then we can draw a straight line. But if we can't draw like one line or not the same functional relationship anymore, but if it changes discontinuously here, we would have a problem. So kind of the assumption is that it's really those below and those above the cutoff. That's kind of a bit of random. What kind of breakfast someone had at the moment. That this brings her or him above or below the cutoff. It would be different if it's really possible to manipulate the cutoff. So if the teachers know the cutoff, for instance, we might have a problem that they say, okay, I basically want that everyone receives this, or many people benefit from this remedial education. So that means basically there are no observations here, because the teacher sets everyone down, or makes difference by socioeconomic status. That would be a problem. So what we basically assume that all the covariates that they develop smoothly across that cutoff. And if the RD really worked, that's not a very strong assumption in my view. Because if the cutoff is really external, cannot be manipulated, then it's a kind of randomization that we have here. But we need to assume that nothing else changes at the cutoff. that there's no other treatment that happens at the same time, and also that all the covariates have a smooth distribution. For observed covariates, we can check. So if in our data sets there's a proxy for parental background, we can actually really examine this graph, or run the respective regression. And then we basically want to see there's no effect of the cutoff on the socioeconomic status. That's what we can only do for the observed characteristics, but this is something that's expected from RD papers. That they show, at least with respect to observed covariates, there's no discontinuity. It's not a proof for the identification assumption that nothing else changes at the cutoff, but it's good, provides additional evidence that's likely true. Why is it not a proof? Well, there might be unobserved factors. They could, in theory, change discontinuously at the cutoff.
But how realistic or how good of a model is that if, for example, because I would imagine in our example with tutoring that teachers would target extra resources to like borderline students, for example, like then our RDD, I don't know if this would make a lot of sense, because then our assumption wouldn't hold, because it would be manipulated, right?
Exactly. But that's something that I like a lot about this regression discontinuity design, because the data tells us if this kind of manipulation happens. If this kind of manipulation happens, we should see that the covariate distribution is not so smooth here. Or what researchers usually do, they plot the density of observation, so kind of the number of observation in very tiny windows around it. And they also, if you see then the discontinuity here, at the number of observations or the density of observations, that's evidence for some kind of manipulation. However, if that's very smooth, then this provides kind of strong argument in favor of the assumption, saying, hey, if there would be manipulation, we would have to see it in the kind of density or the number of observations that we have there. And this is what I think makes it a very strong strategy for the identification of cause and effect, because the data tells you actually when it goes wrong. So there are a couple of tests or additional analysis that everyone expects researchers to do, like plotting covariates, plotting the density or the distribution of observation around that, where people would see, okay, this is fishy, something else is going on. Again, we can't prove the identification assumption, but we can make it here very plausible that works with these data. Further questions so far? So this was like one way of teaching RDD without slides. I also prepared some slides, I uploaded them, so I will now make another tour, maybe a bit quicker than usual, through all these slides. So there will be some repetitions, but maybe some of the information are new. What will be new? So far, I basically presented regression discontinuity design as a graphical tool. I just drew graphs. And the graphs are kind of, I think, really an asset for regression discontinuity, because everyone expects you to, as a researcher, to present these graphs. But graphs are not kind of the only way to show results of the regression discontinuity design, but as the name indicates, regression discontinuity, we can also formulate this in a way of a regression. And this is kind of what we will be new in here. So I will first show you the general idea. That's kind of very similar to what we had. Then we talk about kind of examining the validity of the regression discontinuity design, so that kind of links to your question. How can we provide additional evidence for the identification assumption? What's actually the identification assumption? Then we will discuss discuss various issues and then come to examples. So you kind of have already seen most of these recommended readings. And the third one here, a survey article by David Lee and Thomas Lemieux. That's kind of new, and that deals specifically with regression discontinuity. And if you have to apply that in your master thesis, RD, then I think this paper is very helpful. I mean, it's already 15 years old, but as a starting point, it's very good. Okay. You always need to find some applications where you have this a running variable and then some kind of discontinuity in the treatment probability. And I think that's kind of a crucial element. And you can't apply it for any research question, but you need to have this specific setting. But the more you think about it, the more examples might come to your mind where this is in fact the case. I don't know whether you know how study places are assigned in Germany. Assuming like a study program, a bachelor's program is oversubscribed, so more people want to study than actually can do. What's kind of for bachelor programs a very common procedure is to look at the high school GPA, Abiturschnitt. And here you can basically think of there's a person with an average GPA of 1.8 and another one with 1.9. So you might argue they're very, very similar. Just one gets the offer of the study program and the other one. And then you can use this to exploit what's the effect of having, I don't know, a bachelor in economics from Free University compared to not having it, or having it from an alternative institution. So the point is here, okay, there's again this rule-based world, and there might be discontinuity in the treatment probability that you have, that you see here. And I would also present some further examples from education context. And to give you ideas where these and so we use this cutoffs and this rule as a kind of experiment, as a kind of local randomization. Here is this distinction between the sharp regression discontinuity and the fuzzy regression discontinuity, where the latter, in my view, is clearly more common, where the treatment probability does not change from 0 to 1. But kind of a bit. And it's important that it's a discontinuous change. So I mostly use the term running variable, but I also wrote down, I think, assignment variable. And some people also refer to it as the forcing variable. All of these means the same, but it's a kind of very crucial element in this RD setting, because that's kind of the horizontal axis that we have. And this is the variable to which the cutoff refers. So the cutoff determines if it is below and above, with respect to this assignment or running. So you would see this RD has similarities to many other designs, in particular to randomized controlled trials, exploiting this exogenous variation, kind of local randomization. But I already mentioned that it has many similarities to instrumental variables. Or my view is actually that RD is a specific type of instrumental variable. I would elaborate a bit more on that. Okay, so here, you see a graph that's more nicely illustrated. We have here the assignment variable, or forcing variable. And here, when you see RD graphs, it's always crucial to make sure, do we have the treatment probability or some kind of outcome measure? And here in this example, we see, it's the outcome variable. And we see there is a kind of discontinuity in the distribution of our outcome variable at the cutoff. So that would be evidence that being above the cutoff increases our outcome variable, whatever that would be. And now, so left and to the right hand side, I always make like straight lines. But regression discontinuity is not limited to the case that we have here to the left and to the right, that we have here straight lines. That's more flexible. We can also work with higher order polynomials of the assignment variable to the left and to the right. So in theory, we could also kind of do some kind of second order polynomial here. And here as well, we could model that, or we could even have like some very flexible functional form. All of this is possible. We'll discuss what are the pros and cons of these different ones. So kind of a common way is really this linear way, and then showing the robustness exercise that at least a quadratic fit separately for the left and for the right does not change the results very much. Okay. So, as with the other identification strategies, here we also talk a lot about the identification assumption. And here the assumptions are that nothing else changes discontinuously at the threshold. And nothing else refers to both observed variables and unobserved variables. For the observed variables, we can basically check, but we can't look at that for the unobserved variables. Therefore, it's an identification assumption that we cannot test. But we can make it more plausible by showing that at least with respect to observed characteristics, nothing else changes discontinuously at the threshold. Then, second assumption, it's called individuals cannot sort around the cutoff precisely. And with individuals, that could also be the teachers or the graders of the test. So, of course, in the example that I had with the test scores, individuals with higher test scores, they of course score better on average. However, it's not possible to kind of, that's the assumption, to manipulate the cutoff in such a sense that you manage to, that you can be sure that you will score exactly above or exactly below the cutoff. So that means so individuals cannot sort precisely around. There's some kind of factors that we can't influence, basically. And then we need to kind of choose a specific functional form of the running variable. RV is my shorthand notation for running variable. So all of this kind of means just because there's a discontinuity at the threshold with respect to the treatment probability, it does not mean that we have a valid RD design. So it can be that there's some manipulation going on, that we will sort precisely around that, or that something else changes at the cutoff. I remember when I was a PhD student, a colleague of mine, he really analyzed that looked at the size of communities in Germany. So when the size of a community, so a city, exceeds a specific threshold, let's say 100,000 individuals, inhabitants, then, for instance, the mayor gets more money. So when you're the mayor of a community with 500,000 or 30,000, kind of your salary depends on the size of the population size of the city that you're in. And then kind of here we can assume, or analyze what's the effect of major salary on the performance of the mayor. And then you can say, okay, there's some, the salary increases discontinuously at this threshold. Yeah? The problem was that at this cutoff, let's say 100,000 individuals or 500,000 individuals, many other things changed as well. And it's not just that the mayor got more money, but also that kind of the community parliament or the city parliament became much larger. They became different type of funding, and they the cities also were allowed to have like specific buildings, more specific buildings like hospitals or universities. So the problem here was okay. There is a discontinuous probability. But there's a discontinuous change in the salary of the mayor at the cutoff, but many other things changed as well. So there were co-treatments and things that happened at the same time. And then it could be that, so let's assume our graph looks like this, but we only fit a local linear regression. Maybe separately for both cutoffs. Then we would have lines like this, and then we would overestimate the treatment effect. So that would be a problem. This problem can even be more severe as here. So again, you see here's already kind of a straight line fitted. But you see, in fact, there is no discontinuity if we manage to find the right functional form of the relationship between the running variable and our left-hand side variable. Because if you see here, so the linear approximation is not right, but if we use this approximation, there's basically no discontinuity in the treatment probability. So here we basically have the wrong functional form and would make misleading conclusions. Basically here there is no discontinuity in the treatment probability. It increases strongly around the cutoff. However, there's no discontinuous jump if we model the relationship correctly. So we don't have the first stage, we don't have a discontinuity, and we just use the wrong form. Okay, now there's a bit more of formulas here. So we somehow need to model the relationship between the running variable, which we call x here, and our treatment variable. D, we assume is binary here, and later also between the running variable and our outcome variable. And what we do here, and that's kind of as bad practice, we don't use like a global model, but we use a separate model for the left and for the right of the cut. What does that mean? Well, we have here some kind of a functional form. In the simplest case, that would be alpha plus epsilon. That would be kind of a linear, but kind of what we assume or what we allow. And here you see there's also a linear form, but I called it alpha 1 plus beta 1 xi. And in the first case I called it alpha 0 plus beta 0. Kind of what we usually allow for, that these alphas are not the same. So in general, the two alphas don't have to be the same. So what it technically means is we estimate, we include the linear term for the running variable to the left, and we include the linear term for the running variable to the right. How do we do that? Well, we include it once linearly, so we include x, and then we also have x being above the cutoff as an interaction. That would be be kind of the simplest case, the linear function. Sorry, but we can also, yeah. So there's epsilon. Yeah. Do it in a bit. We could also use kind of a second order polynomial. Okay. So this is now gamma 1 times xi squared. And above it's gamma 0 xi squared. And that would be kind of the second order polynomial that we have. Yeah, and these gamma 0, gamma 1 indicate that these are different coefficients, whether they're to the left and to the right. Yeah. Now, of course, now you can kind of make use even more flexible functional forms, and we could also include like up to polynomial order of order 3, order 4, order 4, whatever we do. So this is just a very generic way of writing. So there's a specific functional form of the writing variable, and that's different to the right and to the left. And in fact, local linear regression and local quadratic regression are the most common options. With local linear, local quadratic, I mean, it's local linear is we have the running variable enters linearly and linearly interacted with being above the cutoff. It's a linear model. Our running variable just enters linear, and it's a local model because we say okay, it's different to the left and to the right of the pattern. And you can do the same with local quadratic regression. And actually, the recommendation is to use either local linear or local quadratic regression. Meaning we should only include up to order 2. Otherwise, we have a problem with overfitting. Okay, so what we did not talk about yet is kind of the bandwidth. Because here we basically assume that we use the bandwidth, the whole observation window. Going from x equal to 0, this x equal to 1. And in fact, most papers don't use, RD papers don't use like the complete range, but they usually go for a specific bandwidth. So here we could say the cutoff plus minus 0.25. So then you could say, okay, we are only looking at these observations here. And because we're not that much interested actually in the observations that are further away from the cutoff. We're basically only using them to get at an estimate for what's at the cutoff coming from the left and coming from the right. The problem is just we don't have enough observation here around the cutoff. And therefore we need some of the observations that are kind of close to the cutoff, but not exactly at the cutoff. And then we could do here local linear regression or local quadratic regression. And then you see that there are some procedures to select the optimal bandwidth. They say, I mean, this was kind of arbitrary that I drew it here. And this is also kind of what researchers do. Then they say, okay, I make the bandwidth here, then I make it put it to here, then to here, and look whether the results change. That's one way to do, and then there are kind of specific procedures that call for, that search for a kind of optimal bandwidth. Optimal with respect to some kind of variance reduction, not with respect to the result that we get in here. And then we can say, okay, we did not select this bandwidth, but the computer selected that bandwidth. And you see this also in some applications. Okay, so this the key point second part of the slide is that fuzzy regression discontinuity is an instrumental variables approach. Yeah? So, what's our instrument? The instrument is basically being above or below the cutoff. Yeah? So it's a binary instrument usually. Yeah? However, in this instrumental variables approach, we have to control for one covariate, and this covariate is the running rate. Yeah, because we know that individuals to the left and to the right, they differ by the cutoff. They differ by the running rate, by the forcing rate. And we want to kind of basically control for that, linearly or quadratic. Yeah? But apart from that, it's a we can also write it down as two-stage least squared. On the left-hand side, the first stage is d is equal to, I don't know, do I have more, just delta 0 plus delta 1. How do we call that? So where did I go? The first stage is our treatment is equal to some constant, and then we have this delta 1. Delta 1 is an indicator variable for our x. The value of the running variable is larger than x0, the cutoff. And then we have, that's kind of the instrument that we have here. And then in the second stage we have now y. Then we have new second, then new d hat. And so we use the prediction from that. And then we have an instrumental variables approach. Now we can interpret this as an instrumental variables. And the first stage, we have an indicator variable of whether someone is above or below the cutoff as the instrument. And then we predict the probability to be above or below, of whether you have the treatment or not. And then include this predicted probability in the second stage. Remember that beta IB is beta, that's hard to read. So our instrument variables estimate is equal to the intention to treat effect, ITT, divided through the first stage effect, or we also call it reduced form divided by first stage. And in the context of the regression discontinuity design, the reduced form is the effect of being above or below the cutoff on our outcome variable. This one. This is the reduced form. It's the effect of our instrument being above or below the cutoff on our outcome variable. And this is the effect that we need to scale up by the first stage. That's what the instrumental variables interpretation says. Why? Well, because here at the cutoff, only some individuals change their treatment status. It's not a sharp RD. It's a change in the probability. And therefore, we need to scale up this small difference here by how many people actually, what's the share of people who change their treatment status due to our instrument. Due to being above or below. So fuzzy RD is an instrumental variables approach. However, in empirical applications, it's not always analyzed that way. The reason is that sometimes researchers don't have access on the first stage. And then they present basically reduced form effects or intention to treat it. So I do research in economics of education, but I also do research in health economics. And there kind of many papers deal with the question of alcohol consumption, and particularly with the effect of alcohol. Yeah, we can connect it to education research actually, because there are also some papers that look at the effect of alcohol consumption and educational outcomes. The problem is there's a lot of selection, and who consumes alcohol and how much do these individuals consume. That's a choice of the individual, so it's not really random who does that. However, in many countries, there are minimum legal drinking age regulations. And in some countries, these are really strictly enforced, or rather strictly enforced. So in Germany, for instance, you are allowed to drink beer and wine as well, only once you turn 60. So with 15 and 364 days, you're not allowed to legally consume or buy beer and wine, but with 16 years and 0 days, you are allowed to. And then, so this means there might be a discontinuity in the propensity to consume alcohol at the threshold of the birth. So there's another cutoff at 18 in Germany. In other countries, these are different ages. But the general idea is, okay, from a specific point onward, you're legally entitled to purchase alcohol, and therefore more likely to consume it. Of course, there are some individuals who consume alcohol before, and there are also some individuals who never consume alcohol, neither before or after the cut. So therefore, this would not be a sharp regression discontinuity design, but more like a fuzzy regression discontinuity. But then, the reason why I'm putting this here is what the researchers usually look at is the effect of being 16 years old versus not 16-year-old on alcohol or on test performance. That's performance in tests. And because usually we don't observe the exact alcohol consumption of individuals. Or there are also other problems that people don't really report the truth about. Some people might exaggerate what they consume. Others might report true though. Therefore, in a case like that, focus would be on the intention to treat it. Okay, that was the general idea of the regression discontinuity design. Let's now come to providing a bit more evidence for the identification assumption. And this can be done with the graph. So for the validity of the regression discontinuity design, we first of all, we need the first stage. We need a graph like this, or when we do it in a regression, we need that the cut being above the cutoff has an effect on the probability to have the treatment. Here's the D. We need to have, otherwise we don't have a discontinuity design if there's no discontinuity in the treatment probability. We have no instrument. So this is kind of, but this is not really an assumption because we can test it. Then, that's the first stage. So that's similar to the relevance condition of instrumental variables. Here, W are observables. So we make the assumption that nothing else changes discontinuously at the treatment. Nothing changes discontinuously at the cutoff. The cutoff here is always centered to have B0. And here, this is what we have to show. With respect to W, the observed covariates. And is something that we can't show. Yeah? So we show basically the average of some unobserved variables to the left and to the right of the cutoff. Yeah? We can't show it because U is unobserved. Yeah? But we need to assume that it follows this way or some other smooth function. Yeah? So you see that there's a different function of relationship between W and X than between U and X. And so this has a slightly different form than that. So the key point is that can be completely different functional relationship. The key is we at the cutoff there should not be a discontinuity. That would be indicative that something else changes. And kind of this is usually what so when you see an RD paper, you should expect to see some kind of this first stage graph, or and put in a regression, and you should also expect some kind of showing that there's no other observed covariance change discontinuously at the and this can be either done with respect to graphs like here, but we could also do a regression. Basically where we put on the left-hand side of the equation W. And there we want to show that being above or below the cutoff has no effect on W, once controlling for the running. Okay. Okay, I think that these are the 2 points that I just made. You can either do it graphically or you can do it with a regression. And here I call it the seemingly unrelated regression because W can have multiple, or include multiple variables. And what we want to say is that our discontinuity should not, being above the cutoff, being above or below the cutoff should not influence variables gravity. And then what you should also do, what researchers should do, so that they're not able to manipulate the running rate. And the sign for manipulation would be if individuals many more individuals are above the cutoff, just above the cutoff, than individuals are just below the cutoff. If there's some kind of discontinuity in the density. And you can do that graphically and plot the density of the observations around the threshold, or you can perform a manipulation test developed by Justin McFly. Okay. Regression discontinuity approach shares features with other strategies to identify cause and effects. Again, with matching, we're trying to compare similar individuals, and we argue those below and above are similar. We discussed at length the relationship between fuzzy regression discontinuity and instrumental variables. And RD shares also a lot of similarities with randomized controlled trials. We expect that there's some kind of randomization around the cutoff. It's a bit of random, who's just below and who's just above the cutoff. In general, regression discontinuity is a graphical device, or also a graphical device. So when I see a regression discontinuity paper, then I basically want to see specific graphs. Maybe also or the corresponding regressions as well. First of all, I want to see there's a discontinuity in the treatment probability. I want to see there's a first stage. Then I would like to say, is there a change in the outcome variable at the threshold? So this is not relevant for the design, but that's relevant to answer the substantial research question that we're asking. Then show that observed covariates, that they don't change discontinuously at the threshold. And further, show that kind of the marginal distribution of the running variable is smooth around the threshold, showing that there's no sorting, no manipulation. I think I brought you like one figure that looks a bit strange, but this kind of contains all these graphs basically that I want you to see. Okay, this is a example from political science. And here, that also economists job. And here the question is, what's the advantage of being the incumbent, der Amtsinhaber, in an election? So assume there's an election for a mayor or for a congressman in the US, and there's someone who is the incumbent, so has already been the mayor in the previous legislative period, or the member of Congress before, and people are running against it. How is there an advantage of being the incumbent, and if yes, how large is that? The problem is also the treatment is not, being an incumbent or not, is not randomly allocated. So when you look at the US, in some states, the incumbent is always kind of, like in New York City, for instance, the incumbent is usually always from the Democratic Party. So kind of there are specific districts that always lead to specific parties. So it's not kind of random who's the incumbent. However, what political scientists and also economists use, they look at the victory, at the margin of victory in the previous election. They show that there's some constituencies or some elections where there are just a couple of votes, in the extreme case just one vote, that one person became the mayor or the member of the Congress, but not the other one. And this is kind of what they exploit here. Here on the in all these graphs, we have here basically the margin of winning in previous elections, and then kind of this for the substantial research question. This is the crucial graph because it shows that individuals who are just above the cutoff here, they have a fundamentally higher probability to win the next election. I don't know, but it seems that it goes up almost by 50 percentage points, maybe 40%. So that would be kind of evidence for a substantial treatment effect of being the income. And here is just kind of the regression function for some covariate that they have here. And below what you can see is also the density. And we basically want you to show that there's no, there's no manipulation, that also kind of around the cutoff there's a smooth distribution of observations. And here you see some kind of these lines here. They basically refer to the bandwidth that will be used for the regressions. Okay. I already discussed that in RDs they generally two broad options. So, and how to control for the running rate. One is we could include a polynomial of order 7 or order 8 or even higher. So very flexible function. And then kind of use raw bandwidth or look at all the observations. An alternative would be, okay, we take a smaller bandwidth around the cutoff, and then only use local linear or local quadratic regression. So just a linear or quadratic structure. And Gehman and Imbens, they make a very strong point that one should go for the small local approach for this one. And this is kind of generally followed. That makes a lot of sense because when you include like a polynomial of order 7, of order 10, then you might get some very strange functional forms that might also capture the tries to capture the discontinuity that you have. Or the results might be very unstable, depending. And then observations so very far away from the cutoff, they might receive a lot of weight in these. And therefore, kind of the generally recommended approach is to get to use a more local approach. Use a smaller bandwidth and then a lower order polynomial. So first or second order. Okay, and this is kind of the paper where I write it. Then some more recommendation is transform the running variable cutoff at 0. This is kind of what statistical software automatically does. Let the regression function differ on both sides of the cutoff. That's what we discussed here throughout. And we could also think, okay, well, we can just take like one global regression, which is not kind of where the running variable is not interacted to with the cutoff. But this is not the best option. And this other one is way more flexible. Why do we do not have to restrict that the slopes are identical on both sides of the cutoff. So when we model it with different regression functions on both sides, we're very more flexible. Generally, if you have such a paper, so kind of choosing a bandwidth, somehow arbitrary. So kind of what most RD papers do is that they show that this decision is not crucial. They show results for different bandwidth. Usually they also show results for local linear regression and local quadratic regression. And then kind of the last recommendation on this slide is do not just present regressions when you have an RD approach, but also show graphs. Because as Lemieux and David Lee state, the main virtues of the regression discontinuity approach is that it can be naturally presented using simple graphs, which greatly enhances its credibility and transparency. And I think this is what I try to convey to you as well. I show that these graphs, there's no complicated math involved at that point. And this also helps to communicate it to policymakers. Okay. Let's come to, I think, 2 examples here. First one is actually a paper of my colleague Natalia Danza, where she looks at the effect of parental leave on informal childcare and long-term child outcomes. This one is published in the journal Few Resources and applies a regression discontinuity approach, and it combines it actually with the difference in differences. Okay. It's a policy in Austria that extended paid maternity leave. Women who got the baby before the policy, they had 12 months of paid maternity leave, so they received a fraction of their income from the previous job during that period for 12 months. But after the policy, this was extended to 24 months. So women then received a fraction of their wages for 2 years, basically. So it made it kind of more attractive to stay longer in maternity. And now what does that have to do with regression discontinuity design? Well, that's in here. So when your child was born on the 1st of July 1990, you were subject to this 24-month. When your child was born just 1 day earlier, the 13th of June, you were only entitled to 12 months of that. So there's a clear discontinuity in the treatment probability, the probability to have 24 months of, or in the length of paid maternity. Okay, so that's the setting. What, in terms of manipulation,
Shouldn't not be worried. The concern should be that that how to maintain like up to 6 months.
Say again, to maintain up to
6 months. Because yeah, okay, there is no 6 months. Oh, sorry. So it's from starting from 12 months. Oh, okay, yeah.
to 24, yeah.
Yeah, okay. So
So and then
also, so it's 18 months. So 18 months. So 1/2 year. So I think it could got problem and it should be concerned up to the 18th month.
okay, so here it's from it's just the maximum duration that individuals were entitled to. Sorry, I'm just putting that. But it means they were not forced to take the 24 months. They could also take 18 months, or they could also take just 6 months.
Mm.
So their choice was not limited. From below, but from sorry, where's the nice?
No worries, it's alright.
Let me see whether I will find a solution for that. Oh no, it's got very dark. Why can't I move this? Because it's fixed, right? Sorry, then it's dark in here. Do you dare to press on one of these buttons to see whether that works? Okay, so when it's about so the validity of this ID approach, what could be potential concerns here? So mothers who gave birth on the 1st of July or later, they received up to 24 months. Mothers who gave birth before only were entitled to have 12 months of paid parental leave. What could be potential threats for the validity?
For example, that the payment will be not reached in time, or the job could be lost.
The job could be lost?
Yeah,
Okay.
and so that.
So that could be like one concern, that a job could be lost. So if it's before birth, they could also lose the job. The kind of the assumption is that women who gave birth just before or just after the 1st of July, they had similar probabilities to lose their jobs beforehand. It might be that, you might also be worried that kind of there's an effect of the policy on job losses, but here it's basically job protected maternity, so they would have the chance to keep the same job. And otherwise that would be kind of part of the decree. But I'm more thinking about like this, the overall design that we have, the overall identification as such. So, in terms of manipulation, is it possible to manipulate the cutoff? You're shaking your head?
No, it isn't. I would say
It is.
I mean, you can't really delay the birth.
Oh, but you can do it earlier, or when you do a cesarean, so a C-section.
Yeah, but not later. Not later.
Hmm?
I would say not later.
Yeah, but you could. So usually you would take a cesarean, a C-section,
Yeah,
on the 15th of June. But now you say, oh, I want to do it like one day later.
Oh, yeah.
Then I have it on the 1st of July. So this is the way economists think, and when they're the audiences. So now would say, okay, it's not possible to do that. But actually, there's some colleagues of mine who have a paper where they show that when in Germany parental leave was extended, or some other child benefits, then suddenly there were many more births just after the cutoff. I mean, it's, of course, not everyone does that, but it's not that some people do that. So C-section, so planned manipulation could be even here a concern.
I don't know when the policy was told to the people was implemented, or when did the government say that it is implemented? Because the planning of a birth 9 months before could also be like delayed.
Exactly, and this is exactly the right way of thinking. So think the government announced this 1 year before it actually came into place. And then parents might have, they could sort strategically around the cutoff. That's how economists would frame it. But kind of normal people would say, okay, they could kind of delay having the child. So making the child. They could start later with the production process of the child. So that even when you think, okay, birth, that seems to be like very exogenous. The way economists think, and I think that's very good. Way of critically thinking about it. Aren't there some ways to manipulate that? I mean, it's like it's not so little money that we that you would receive. So the extension is kind of a very here. I think it was announced like 3 or 4 months before. But that means so that was where the babies were already underway. So that's where that kind of manipulation could not happen. But the C-section manipulation, cesarean section, that could still be an issue. And what my colleague Natalia Danzer and their co-authors did is that they basically did what's called a donut specification. You know, a donut has a hole in the middle. And so here they excluded specific dates around that cutoff. So they included maybe 3 days or 5 days on both sides of the cutoff to say to see whether the results are comparable. And this is how it often works in applied economics. That someone comes up with an alternative explanation of the results that you have, and then the researcher try to find a way to address this issue. For instance, with this donut specification. Could you think of another threat to the identification here? So one threat is kind of manipulation of the threshold. Another threat is that there's a co-treatment. So what the researchers would have to do, what they actually did, is they don't have to search for whether there are other policies that were effective on the 1st of July 1990 that affected either mostly the treatment or the control. Sorry, because it's just before and after. So that's relevant to the outcome there. Because if there's another policy, like let's say I don't know, some other labor market or child benefit was increased by 10,000 euro at the same time. I'm just making this up, but then we wouldn't know are the effects that we look at really the extension of maternity leave, or are that increases in child benefit, kindergarten. So what you would always have to look in these cases is whether there are other things happening at the same time, whether there are co-treatments, other policies that were implemented in the same time. And another worry that the authors have is that there's some kind of seasonal differences. So children who are born, let's say, in spring, they might come from different households compared to children who are born in autumn. So there are seasonal differences. When kind of high SES and low SES couples mate. So there might be seasonal differences, and this is kind of where this combination with the DID comes from, with the difference in difference, because what they do is that they basically can look at the same discontinuity in a different year, which I find a very nice feature of this research. So here, that's the average parental leave duration. That's kind of the treatment that we have. Yeah? We're interested in what's the effect of parental leave duration on some kind of outcomes. The problem again is parental leave duration is usually endogenous. Couples decide how long they want to take it. But here with the reform, the idea is we have an instrument, we induce and we find exogenous variation. And these are kind of what we have, what we see here now. That before the reform, they just took on average 300, 40 days. And after the cutoff, it was about 650 days on average. And you see that the slope parameters here basically they don't change that much across the running there. And you also see that they have a very narrow bandwidth because they're just comparing individuals who were born in June and July of that year. So just 2 months. And still they have enough kind of statistical precision to measure this exactly. So they have kind of a huge data set, which is often required for regression discontinuity. So here we have the jump in the treatment probability, and this is a kind of falsification exercise to the right of placebo. In 1989, there was no such policy. So there was no extension. If we saw this continuous change in the average parental leave distribution, then that would be kind of evidence that there's something else going on, some seasonality patterns, but they see there's basically nothing. Okay, so that was kind of the first stage, and now they look at some outcome variables. For instance, here again they needed large data sets, so here they had some measure which they called fit for military.
Is that there some compensation for the, is that this kind of parental leave count as the compensation? Or if this not compensation, I hardly imagine that if so many days that they are not at work, and so how can this kind of big discrepancies that be kind of made that equalized, so to say?
Yeah. So I don't know the exact institutional details, but I think it's similar to what was in Germany, and then in Germany there's a kind of replacement rate of 60 or 67% of the income from the last year that you had. That's kind of what you get as paid parenting. So you got a bit less, but you do not have to work. So that's kind of the replacement scheme that you have in there. It's not fully compensating, but it still seems to be financially attractive. And here on this slide, they look at outcome variables, and then they first find basically a zero effect on outcome variables. But then when they look, they see here on the right-hand side, they find effects when they only look at communities where there's only informal childcare. So here, kind of the story then is that it only had an effect, extension of maternity leave, positive effects, when the alternative would be informal childcare. When the alternative would be kind of formal childcare, like in kindergarten, in CDC, early childhood education care facility, there wouldn't be such an effect. That's kind of what they show here. What they also show here is kind of the specification before I showed you a bandwidth of 30. So 30 days before and 30 days after the cutoff. But they basically show, okay, this is not driving the results. We could even select 2 months on both sides. Then we would get very similar point estimates, just that the confidence interval gets smaller and smaller. Similarly, they could even go through 50 days before and after, and would still have similar effects, just the confidence interval gets larger and larger. And this kind of what people expect. Very last picture for today. This comes from a work in progress project of myself. Here I look at school entry cutoffs in Germany and most countries. all countries have school entry cutoffs, where they say, okay, children who turn 6, 7, whatever, until that day, have to, or should enter school in a specific. And here, and this is kind of where you're looking, this is the cutoff. So these are children who were born just one day after the cutoff, and here children who were born one day before. Children who were born one day after the cutoff, that means, okay, they enter the school in the next year. So 1 year later than these. Additionally, those who were just above the cutoff, they are the oldest in their class. Because they're kind of the first in terms of the age. I mean, there's some people who repeat grade, but generally they're among the oldest, whereas here they're among the youngest. It also means that in a school class, the children were about almost 360 days different in terms of age. And teachers often don't know the exact age. But I don't know whether any one of you has children. 1 year difference in age of children is a lot. So there's a lot of the development that they're already. And this is kind of what we see here. Here we have whether someone attends in the secondary school at least a Realschule, a middle track school, or a gymnasium. And what we see, and what we see in many data sets, is that individuals who are born just above the cutoff, they have a clearly higher probability to end up on at least, not on Hauptschule, but on Realschule, middle track, or high tracks. And you see similar discontinuity when you only look at individuals who go to, or when you only count individuals who are at the high track gymnasium. We're not the first to show them. But this, I find this very, very, very striking. Because again, here these are basically days that